office, I looked up all possible reactions because he has a program to do that. And is there a possibility of platinum being involved? That is, somehow platinum interact with proton, somehow overcoming proton barrier. And that can give like silver and germanium, as well as if you invoke oxygen, oxygen and carbon in plastic, then you can cover most of the product you have seen without invoking negative Q bar.
I don't think you can reproduce these four hump curves of platinum. And when you look at the amount of material that's produced, in fact, I didn't have that much platinum to start with. I think that you're looking at the wrong starting element. Platinum can't be the fuel. It has to be one of the major components in the cell. In addition, I didn't have time to go into it. We have run some cases platinum electrodes to compare with the titanium electrodes that are shown here. Anyway, I have no evidence it could have been platinum. I think great speculation has to be put into this. As I say, again, though, the characteristic that this four hump curve is very hard to reproduce when you look at all when you look at all the elements. If you look at this, one reaction produces 3 or 4. It's very hard to do it.
Okay, I think the time is limited, so we will accept 2 more short questions.
Yes, with 50% product yield, you should be able to see a reduction of the nickel. Did you look for that at all? And if so, that would really be another argument against this being due to impurity accumulation or anything like that.
We're looking at that. However, it's more difficult than it seems because it does vary with the layer and other things. So I don't have a final answer on the nickel balance.
Okay, one more question. Use the microphone, please.
What? Well, I don't know. You might say something. I just told you. Well, if you have a fission event, you'll get different isotope shifts. We don't know until we identify what the mechanism is. So you don't know what isotope shifts to expect. And so, but the fact that they're not natural does give you some encouragement that something's happening other than just impurities on here. Although you could postulate some bizarre isotope separation due to differential diffusion, what have you, if you want to try to look at it from that point of view. That's one reason the NAA results are so important, is they were looking at the isotope shifts averaging over the entire body of beads and a large number of beads, even if you had differential diffusion, different isotopes in, they would average that and get the net change in abundance.
Okay, time is over. Thank you, George.
We'd like to move on to the next papers. We'd just like to announce once again that papers 17, 21, and 22 were canceled. So the final paper of this session is number 20. bed flow through electrochemical cell. Authors are Michael Kirby, Steve Housebreaker, Frank Penzella, and Dennis Schrader. Paper will be given by Dr. Michael Kirby.
Contrast to George, I'm going to present something which is rather dull. All I can do is promise not to keep you very long. Since people are so interested in the packed bed flow through electrochemical cells, I took it upon myself to do some calculations on the distribution of electrochemical process inside such structures. We've been working a little bit with the Patterson cells, courtesy of Seti and Jim Patterson. We've configured them slightly differently, but it's basically the same picture as George showed. The electrolyte comes in the bottom, flows up. We've configured our inlet plenum to have a platinum resistance temperature device and a thermocouple symmetric outlet plenum with pretty much the same configuration. What we're concerned with, what this paper is concerned about, is the distribution of electrochemical process inside this packed bed structure. There's an electron contact here, current contact for the cathode, so that current is supplied at the bottom, current flows from the bottom to the top, and the electrolyte flows from the bottom to the top. This can be modeled as a electrochemical transmission line. The first person to solve this system, in fact, was Lord Kelvin in 1855. He solved the problem of the transatlantic cable. It's the same solution, same model. You look at this like a coaxial cable, a transmission line. So there's the resistance of the solid phase. So this is the interconnecting pathway of the solid spheres in the Patterson cell. The thin metal coating on the surface of polystyrene spheres makes a continuous resistance. The electrolyte, as it passes from the bottom of the cell to the top of the cell, makes a continuous ionic conductor through the void space. And distributed in between these two processes is the electrochemical operation, whatever is going on. And in a coax cable, obviously, this would be a capacitor. For an electrochemical process, this is a somewhat more complicated and non-linear thing. What we do is break it up into discrete elements. So we have a distributed interfacial impedance, a distributed solid phase resistance, a distributed electrolyte phase resistance. I can see eyes glazing as I look out. So we have a set of differential equations we can solve for this case. You needn't bother with these at all, except to know that the bottom is rather well known and rather well solved in a rather powerful way of interrogating the electrochemical kinetics of a distributed electrode structure. If we take the parameters of a normal, if there is such a thing, Patterson cell, here we have a bed, a cylindrical bed of known radius containing beds containing beads, microspheres of a known radius. Electrolyte phase resistance, 1 mole of lithium sulfate at 25 degrees. We know its resistivity per unit length. Solid phase resistivity is a little bit more difficult to calculate because you have a thin film of nickel or multiple layers of nickel plate with nickel on the surface of the resin spheres. And the electrochemical process, these things we know very well. The geometry, the resistivity of the electrolyte and solid phase. The electrochemical process is a little bit more complicated. We use a rather simple form, the Butler-Volmer equation, where the unknown is the exchange current density, this pre-exponential term, and we don't really know this. So what I've done is solve this system for a number of reasonable values for the exchange current a parameter which determines how fast the electrochemical process is occurring, in this case the discharge of hydrogen onto the surface of the Addison spheres. So we look at this, we get a solution. Here we look at the bottom. This is the current contact at the bottom of the bed. Here we traverse the bed from bottom to top. This is where the electrolyte leaves the bed and goes on towards the anode. Bed is something like 0.57 centimeters long for this particular calculation. Set of calculations of the interfacial overvoltage, a measure of the electrochemical driving force for any process which might occur. As you can see, for small values of the exchange current density, a rather sluggish electrochemical process, we have a profile with a voltage starting at about 0.36 or so and heading up towards 0.6. If the electrochemical process is very fast, 3 milliamps per square centimeter, which corresponds to quite a fast kinetics. The bottom of the bed is basically inactive. The top of the bed is got an overvoltage of 200 millivolts. As you can see, in all cases, the currents, here's the solid phase current in this case 100 milliamps, enters at the bottom of the bed, and by the time it gets to the top of the bed, all of the current is in the electrolyte and carries on towards the anode, and the value of the exchange current density doesn't affect very much the profile of the current within the bed. We're not really interested in any of those things, especially. And the conjecture, the idea of the packed bed system is that you can achieve very high activities of hydrogen in an extended structure to extend the area of your electrode. So what we're really more concerned about is what does the profile of hydrogen activity look like in such a bed? How much of the bed is likely to be active with respect to any electrochemical or potentially hydrogen-driven nuclear process? We can know this reasonably well. We observe that there are some good fundamental reasons to expect that the loading, the hydrogen to palladium or deuterium to palladium ratio, in this case the observation by Hasegawa et al. In the Kunahaku's group, and also our own observations, that you see approximately logarithmic functionality between the D to 3D ratio, atomic ratio, and the log of the current densities. So we've calculated the current density. All we need to know is the coefficient gamma. What Hasegawa et al. Saw was approximately a 3% per decade increase in the loading. What we see is that there are really two cases. For palladium electrodes that behave well in deuterium electrolytes, we see about a 6%, even 6 to 9% slope per decade. So we've chosen two limits, 3% per decade, which indicates a rather poor performing electrode, 6% per decade, which indicates a rather well performing electrode, and we make three, on the surface of it, rather extreme assumptions. That the palladium coating behaves similarly to bulk palladium, it's probably reasonable. That cathodes in light water electrolytes flow similarly to those in heavy water electrolytes. It's possibly true, but I certainly know some exceptions to this. But the current density loading functionality in 1 mole of lithium sulfate is similar to that in 1 mole of lithium hydroxide. I really don't know about that very much at all. And to proceed further with this substantively, one would have to test that assumption. We make those assumptions and perform a calculation to indicate the shape of the hydrogen loading profile within that packed bed structure. I've done a calculation in one particular case for 100 milliamps being passed in Jim Patterson's or George Marley's cell for an exchange current density of 1 milliamp per square centimeter. If we have the loading, current density functionality that Hasegawa et al. Saw and that we see corresponds to rather poorly performing cathodes, poor is a poor choice of word, draw some conclusions. Calculations were performed for a rather short bed, only 0.57 centimeters long. This bed, nevertheless, exhibits substantial dispersion of process. Only the top of the bed is really active. So extending the length of the bed doesn't bind very much at all. Because of fall-off and activity with distance from the end of the bed, there is really no reason to double the length of your pattern cell. You don't get any benefits from it at all. I don't know whether Jim Patterson knew this or not, but in fact, the dimensions of his bed are rather comfortably and suitably matched to the distribution of the process inside the bed. If you use these, if you use this model, the free-scaling dimension is in the radial direction. So you can make the bed as fat as you like, and this is a direction also that SETI has chosen to embark upon, either for good reasons or good guesses, I don't know which. Even for thin metal coatings that are used, the metal phase conductivity is still very much more than the electrolyte phase conductivity. So it's the conductivity of the electrolyte which governs the performance of the bed. And by going to very much more concentrated electrolytes, you can somewhat improve the performance of the system. And at the extreme, if you choose the best of the best, if you take the best of my assumptions about the loading behavior and the best of my assumptions about the exchange current density, the electrochemical kinetics, then you can get rather reasonable hydrogen loadings at the front end of such a bed structure. And now I will close.
This paper is now open for discussion. Question, please, in the back. Martin, White.
A couple of quickies. Has anybody tried this fluidized bed? Because the fluidized bed, of course, you can match metal resistivity to the liquid resistivity and extend the reaction domain. What I can do is I could try and take a thought about it. And in the case of the palladium system, of course, as far as heat generation is concerned, you get a very interesting connection with heat after that.
I should back up here and say that 21 years ago when I first met Martin Blythman, I was working on this exact problem at the University of Southampton for rather different reasons. And he was dabbling with fluidized beds. The answer is, as far as I know, nobody has tried it with a fluidized bed, but it's a very good idea.
We got we did get components of the University of Utah to Paris, for of course we ran out of steam then. Right. But it struck me that especially if you consider heat transfer engineering, this is a very good way to push the technology.
And to your question, have I thought about it? The answer is yes.
Do you have any other questions?
Everybody wants to go to bed.
So in that case, then we'll close this session.
Thank you very much. Our next session will be the special session on transmutation, and we would like to welcome Dr. Paso and Dr. Takahashi to chair this.
Okay. Probably want to partially another 35 minutes or so. I'm very sleepy, and you must be also very sleepy. And as the chairman of this session, I can't say you can sleep here if you like. And as I understand, this special session, the papers are usually treated as a post poster papers, but the topics are so interesting, and we gathered some of the papers to make some intensive discussion here. However, because of the limitation of time, each speaker can have only 5 minutes per paper. So we have 5 speakers today. So the first speaker has 2 presentations, so I have 10 minutes. And let me introduce first speakers. Number TS001 and TS002, analysis of nuclear hydrogen isotope system on TM-CF model, and also nuclear transmutation cofusion experiment, presented by Professor Kojima. In 10 minutes, please.
I will present you the 2 papers in 10 minutes. The first one, analysis of nickel hydrogen isotope system on TM-CF model. As it is already common sense that the cold fusion materials are complex systems. So the atomic processes occurring there is stochastic process and world of probability. So we cannot expect the quantitatively produced field, but qualitative. So definite causality cannot exist for those processes. And on our model, for instance, in the case of electrolytic system, the cathode and electrolyte contact with the surface, and on the surface, in the electrolysis procedure, not only the hydrogen or deuterium, but also the electrolyte deposit on the surface. And here appears, for instance, in the case of lithium electrolyte, palladium lithium alloy layer and perhaps metal layer. And those structure, as we shown in the poster session, works to trap neutrons. And the neutrons interact with lattice nuclei and get propelled, becoming stable against beta disintegration and also against fusion with nuclei in the lattice. But the trapped neutron, once suffered with large perturbation, Bush and Eagleton. And second, by Hokkaido et al. And the third, potassium power cell. And the result was here in the table. In the case of Bush and Eagleton, here occurs also the nuclear transmutation I have mentioned later. Number of events producing excess heat is assumed Q divided by pi in million electron volt scale. And nuclear transmutation events, ratio of these events is 3 by experiment. And our theory gives 1. And in the case of potassium power cell, the heat is given here, and the heat predicts the number of neutrons about 10 to 10 per cubic centimeter. In the case of the shield, the number is 10 to the 7. And another case, Okamoto the case, number of neutrons is 10 to the 12. And another one I have to mention here. The data of the group, in this case, they used discharge. The number of neutrons should be 10 to the 9. And next thing is the nuclear transmutation. One already I told you in the case of Bush-Eagleton. The fundamental process, nuclear process, is neutron and nucleus. And our analysis is on the 3 experiments. The first one is Russian Sabatino et al. And the second Ramadan et al. And the third Japanese Okamoto et al. And the result is also in the table I have shown already. In the case of and the Eagleton, rubidium-85 becomes strontium-86, and the ratio of isotope of rubidium and strontium changes. This reaction is explained by that reaction I showed before. And in the case of Okamoto et al., the aluminium-27 changes to silicon-28. And the Sabatino case, palladium-106 becomes silver-107. And those are this very simple example of the nuclear transmutation. But today, chairmen told us they observed heat production in the case of light water. And perhaps it's dependent on...
Could you please conclude
let's see, all of your prediction is based upon the fact or assumption you are making that there are enough neutrons around. And then you're using some of the processes involves weak interaction. And I cannot see where you can get the neutrons. And if you use a weak interaction, rate will be extremely small, so that your prediction may not hold.
No. That is a misunderstanding that the weak interaction is taking part in our model. The model assumes the background neutron trapped in the solid by band structure mechanism. So it is a very natural assumption. Only one question we have to solve is the lifetime of neutrons in the solid. To explain the stability of the neutron in the solid against the beta disintegration and fusion with the lattice nuclei, we propose the neutron affinity of nuclei. This concept have to be proved by nuclear and antibody treatment, and this problem is remaining. We are going to treat this one sincerely from now.
Okay, thank you, Professor Kojima. Thank you very much. Sorry, the next paper, TS003, has topic distribution for the elements above the braided castle of electrolysis in this solution, presented by Dr. Mizuno. In 5 minutes, sorry, 5 minutes.
Thank you, Dr. Takahashi. I'm very happy because my presentation almost over by Dr. Myers. So I'm talking to my result very briefly. Isotopic distribution for the element involved in Halley castle after electrolysis in phase 2 solution. We confirmed by several analytic methods for reaction product on the plasma surface electrolyzed in a heavy water solution. This is a typical EDX spectra before and after the electrolysis. You can see many elements appear after electrolysis, such as chromium, iron, copper, zinc, lead, and also you can see calcium, titaniums. These mass numbers are rated from 1 to 2 over 8. That means from hydrogen to lead. This shows the typical source spectra after the electrolysis. This is the mass number and this is the counting ratio. These are divided roughly 4 groups. Okay. This is very similar with Dr. George Malling's result. Most important fact is large differences in isotopic distribution compared with natural distributions were observed in the depositions. chromium has 4 stable isotopes: chromium 50, 52, 53, and 54. Other surface region, within the 1 micrometer depth, you can see a large deviation from the natural one, especially chromium 52 is very degraded. However, this concentration is approaching natural value towards depth, towards more depth, towards the depth.
In 1 minute.
Okay. This is the palladium result. Palladium has 6 isotopes, especially you can see large increase. You can see large increase occur 104 and 110. You see. You can hardly imagine that all of the elements found impurity in electrolyte, electrode, and cell. Even if we suppose that all impurities in the system accumulated in the cathode, the amount would be 10 to 100 times more than the total amount we detected. Furthermore, it is impossible to explain the shift in the isotopic distributions. We do not know any mechanism that explains such isotopic change by conventional diffusion and electron deposition process. Therefore, it must be concluded that some novel reaction occurred, resulting in the reactions which were found abundant in the electrolyte and electrode materials. It must be admitted that these reactions have no solid, detailed theoretical basis yet, but in broad terms, this can explain most of the reactions which were observed. One may also imagine that such reactions were presumably taking place during the electrochemical process. Thanks.
Did you find any change on the concentration of silver before and after the electrolysis?
Yes, I found a lot of silver. However, there is only 2 stable isotopes.
Yes.
I cannot find any distribution change, isotopic change. That was completely normal in that case.
So you find the change in concentration but not in the distribution?
Yes, no. And distribution was completely decreasing with the semi-values you hit towards the depth. Okay. And the isotopic change was completely the same as you normal.
And did you observe some change in the 108 isotope of the palladium?
108, yes.
Did you observe a decrease or decrease?
108 degrees.
Decrease.
Okay.
Thank you.
Thank you. Thank you, Dr. Let's go ahead to the next. Yes, the production of heavy metal elements and the enormous surface structure electrons produced during the electron electrolysis on gold electrode by Dr. Omori. With 5 minutes.
In the present session, I would like to talk about the work entitled Production of Heavy Metal Elements and the anomalous surface structure of the electrode produced during the light water electrolysis on gold electrode. In previous presentation, in last year's conference held in College Station, USA, we reported that iron permanent from its natural isotopic abundance. After that, we found that porous black or gray deposits were produced by the electrolysis at current densities about 200 milliampere per space unit. Major component was gold. Besides, mercury, platinum, iron, silicon, and fluorine were contained. The isotopic distribution of mercury, iron, and silicon were significantly different from their natural values, and a lot of the microcraters were formed on gold surface, gold electrode surface after the electrolysis. In this presentation, I like to talk about the experimental results. The elemental composition and the isotopic distribution of the elements contained in deposits is very unusual. This is the Ikegama image, and this is Shields image of the deposits, and this is the whole Ikegama image, and this is platinum, and this is mercury image. As can be seen from this figure, the main component of the deposit is gold. So the deposit was produced at gold electrode, we can see. Besides platinum and mercury and iron, hafnium, osmium, and silicon are contained in deposit. This is the isotopic distribution of mercury present in deposit, measured from 1 to 15 scans by Shields analysis. As seen from this figure, mercury 200 increased from its natural abundance about 2 times increase. On the contrary, mercury 200 decreased significantly at this level. This is the isotopic distribution of iron. In this case, the main component of iron 56 degrees.
Sorry.
Basic.
Sorry, please continue in 1 minute.
And on the contrary, iron 57 degrees significantly. And more, in addition, the surface structure of gold electrode after eclipse is very unusual structure. As seen from this figure, such craters is produced. A lot of such craters produced. The diameter of this crater is about 200 micrometers, and the height is 30 microampere per square centimeter. And the structure of crater is very similar to the structure of deposit. So the deposit produced at this crater and spewed out and deposit at the bottom of the electrode. I see. And the numerous components of elements is produced at that part by some nuclear reaction, I think. Thank you.
the contamination of the system due to, I don't know the nature of the cell, electronic cell you are using. It's made of glass, electronic cell. Do you have any contamination from the glass of the cell? Or there some contaminations?
We use quartz glass. So the ability of quartz glass is considered to be very small. In addition, we analyze the isotopic distribution change. In such case, mercury and silicon and iron, isotopic change is very large. So we can't consider that such element come from arsenic. And osmium and fluorine is very rare in the nature. So such element is considered by some nuclear reaction. Not immediately.
Okay, thank you very much, Dr. Onomura. Thank you.
On the next paper is Dr. Matoya from Hokkaido, nuclear reactions caused by electrolysis in light and heavy water solutions.
We have studied the last 5 years on finding the product of nuclear reaction caused by electrolysis by use of gamma-ray spectrometer. The analysis was carried out during electrolysis in light and heavy water of water solutions of all species. All species of alkali ions. Such solutions. We used as a cathode porous nickel and platinized platinum. Each electrolysis was carried out for 24 hours to 200 hours in dark chamber made of real walls of 10 centimeters in thickness, equipped with a germanium detector. This shows a typical gamma-ray spectrum. I'm sorry. We found several peaks due to the intrinsic gamma-ray decay of sodium 22 and 24 in sodium electrolyte and potassium 40 a peak at 511 kiloelectron volt, which must be due to the positron annihilation, was observed also in all solutions used for our experiment. Concerning the source of positron, you see there is here in their products, you see the delta plus theta isotopes. We had found by not radioactive analysis calcium in potassium solution and the species of mass number from 132 to 140 in cesium solution.
About 1 more minute, please.
From these facts, it is concluded that the reaction can be occurring during electrolysis on nickel and platinum. You can see all the reactions can be occurring in a nuclear furnace. Simultaneously, we observe this excess heat mounted from 50% to 200%. After electrolysis, the same electrolytes as used for these observations were analyzed by use of liquid scintillation spectrometer. We found tritium and rubidium-87 only in rubidium solution. But maybe I will not speak about it today. Conclusively, these reactions are occurring as the branching reaction of hydrogen evolution reaction in alkaline solution of nickel and platinum.
Thank you very much. Time for one question. Does someone have a question? Seeing none, thank you very much, Mr. Choi. Since there's no tomorrow, I mean there is tomorrow, but there's no deadline for finishing this session according to the schedule, we have requested from 2 people to give a, oh, sorry, beg your pardon, we have 2 more. The experimental discovery of the phenomenon of controlling and changing the probability and time of spontaneous decay and gamma transmutation of excited nuclear statuses is something. Sorry.
My first report is about the experimental discovery of the phenomenon of low energy transportation of isotopes in growing biology cultures. We have conducted a series of experiments based upon new technology following the precise method of mass power spectroscopy. The experiments based on the expected reaction in growing microbiology culture in heavy hydrous supersalt nitrate medium deficient in iron by additively containing manganese. The direct result is generation of stable rare iron 57 isotope, concentration of which in the natural iron is very low. The iron 57 isotope obtained in small quantities can be easily discovered by means of the mass power effect. is following. It's two cases. First case, it's a case when our source is situated in the center of resonance absorber. In this case, when resonance absorber is situated near end resonance absorber. The red point, it is a result of measure of intensity of gamma radiation. In case when near source there is only resonance absorber.
One more minute, please.
One back it is net non-resonance absorber. As a result of this experiment, one can obtain the experimental value for radiation time. For these two cases, in first case, the radiation time of light was increased to about 2%. In the other case, about 40%. We can also one small experiment by measuring the time of light using the spectral method. Because now what is my time? Okay. This is a scheme of frequency experiment. It is a source of radiation. It is radioactivity isotope stanium 119. It is a resonance absorber. It is diaphragm. It is resonance detector. It is a system of modulation of Doppler velocity. The measurement was realized in two regimes. In first regime, the resonance absorber is situated near real source. In other regime, second regime, the resonance absorber is situated near on the long distance from the source near the diaphragm. It distance near 4 centimeters. In this case, the body angle is blocked by resonance absorber is very great, near 2 pi. In this case, this angle is very small. From other theory, we can obtain other result for spectrum measuring in this case. But in this case, this gravitational quantum is totally equivalent. It solves the resonance absorber, diaphragm resonance detector. Solves the resonance absorber, diaphragm resonance detector. Now it is a result of measuring two independent experimental experiments for this situation. The red point, it is a white of Bauer spectrum. Red point, it is a result of measuring in situated when resonance absorber is situated for long distance from source. The black point, it is resonance of measuring when resonance absorber is situated near resonance absorber. This result, the same result in the case. And it is a result of this experiment. Using the average value for white of power spectrum for first and second case, we can observe the result. In this case, the time of flight, in case when the resonance absorber is situated near source, increased about 20%. Thank you. Excuse me, my battery.
Question right here. Sorry.
I have several questions. Concerning the first one, which was the metrics of your source of iron 27? And from the isomeric shifts and doublets, which kind of compounds do you have?
Yes. It is main information about this. The source was fixed in matrix which has a single line of natural white. There's a matrix, there is type of matrix, I said for you.
The source is only one, I think. The source we are using only one.
One moment, I thought, no. Yes, the carbon 57 isotope with resistivity of 10 military in a chromium matrix was used as source.
how much it was, and which is the compound. In the second, you have a doublet looking as a quadruple interaction. So there is, I don't know, thousands of table of elements, which kind of, to which element they correspond to ranks.
The position, in our experiment, there is not the chemical sheet from the power.
You show.
No, it is very, it's problematic. We use the compound name one moment, calcium O2 and calcium, okay, stannum 190 O2 and calcium O3. In this matrix, there isn't chemical shift between the line of resonance absorption and resonance emission.
Why don't you two get together and arm wrestle this out? And I appreciate the question, by the way. Thank you very much. Before everybody goes off to bed, we do have a couple of requests to do last-minute comments and taken from the chairman's prerogative. I'll give the other chairman the first crack at it, and Shalani would like to give a couple of things. But you are free to go to bed if you haven't reached your limits, of course. Thank you very much. And now I'll go on.
This is very, very old data about analysis by segment in our cell with plastic cell, so long lasting anymore. This is a plate, palladium plate that don't give HSC. So it's after 2 weeks of operation, past operation I found. So just good palladium line. Use like reference. The heavy water is This is with another plate of Tanaka company, born after before it was comes from Ibra materials, and we get gold, actin, iron, copper, zinc, platinum, and so on. It's just a contribution to this new discovery of money from the other people. We get this data in 93, and we just show once in a small conference in Belarus, just 5 minutes, because we don't want to share this strange results, because we are afraid we don't do it as making change.
Thank you very much. I call the meeting adjourned at this time, and we'll see you in the morning. I guess our chairman will tell us when we meet.
Okay, thank you very much, ladies and gentlemen. I'd quickly like to announce that tomorrow's morning session will start from 9 o'clock. And as I mentioned before, there are slight changes in the times of the program, so if you'd like to look at the board outside, you can see the detailed programs. And about the excursion tour tomorrow to the museum in Watermill Park, if you are interested, we'd like you to make a reservation at the travel desk before you join the tour by 12 noon tomorrow. And finally, for poster presenters who still have their posters up in the room next door, we'd like you to remove them before you leave today. And thank you very much and good night.
Good night.